Hello viewers, welcome to Sleepy Mind Channel. Tonight we'll be exploring how to birth a star. Imagine a silence so absolute that it doesn't just lack sound, it swallows it. In the modern world, we complain about a noisy street or a buzzing refrigerator, desperate for a moment of peace. But if you were placed in the interstellar medium, inside a giant molecular cloud, the silence would be terrifying. It is a stillness measured across light years, an expanse of cold nothingness where the nearest atom is a lonely traveler searching for a companion. Yet this terrifying, freezing void is not a graveyard. It is a womb. Every single atom in your left hand, every drop of water in your body, and every rock beneath your feet was once trapped in this exact, silent darkness. To understand how a star is born, we must first understand the concept of nothingness, or rather, the cosmic illusion of it. Between the bright, burning beacons of the night sky lies the interstellar medium, ISM. It is not empty space. It is an ultra-dilute soup of gas and dust. In the neighborhoods near our sun, the ISM has a density of about 1 atom per cubic centimeter. For comparison, a single breath of air you take on Earth contains roughly /BM 2, 5 times 10⁻19 molecules. However, deep within certain regions of galaxies, this diffuse gas begins to pool together, driven by galactic currents, supernova shock waves, and the ancient, lingering sigh of the Big Bang. These regions are known as giant molecular clouds, GMCs. A single GMC can span hundreds of light years across and hold a mass equivalent to hundreds of thousands, sometimes millions of suns. Despite their massive scale, they are incredibly faint and cold. The temperature inside a molecular cloud hovers just above absolute zero, typically between 10 Kelvin and 20 Kelvin /BM -263 /circ /text C to /BM -253 /circ /text C. This extreme cold is not a random byproduct. It is an absolute necessity for the birth of a star. In physics, temperature is simply a measure of kinetic energy, how fast particles are moving. In a warm gas cloud, atoms zip around at breakneck speeds, colliding and bouncing away from each other. If a cloud is too warm, the thermal pressure forces the gas to expand outward, scattering it into the void. But at 10 Kelvin, the dance of the atoms slows to a crawl. The molecules of hydrogen /BmH_2 and helium, along with microscopic grains of cosmic dust, silicates, carbon compounds, and water ice, lose their frantic energy. They stop running away. They begin to feel a faint, subatomic tug that they have ignored for millions of years. Gravity. Think about the coldest winter night you have ever experienced. The way the air bites at your skin, the way your breath blooms into a brief, ghostly cloud before vanishing. We associate cold with death, with stagnation, with the end of things. But in the grand calculus of the universe, absolute cold is the prerequisite for life. Without these cosmic refrigerators, the universe would remain an unending, uniform haze of boring hydrogen gas. We humans spend our entire lives trying to build walls against the cold, burning fuel and wearing layers to stay warm. But 4.5 billion years ago, the matter that comprises our bodies needed that profound, undisturbed freeze. It needed a place away from the radiation of older, raging stars, a sanctuary where it could finally slow down, rest, and gather the strength to fall inward. There is a fundamental rule in human relationships. If you stay apart long enough, you grow distant, but if you get just close enough, a sudden, unstoppable attraction takes over. Gravity behaves exactly the same way, but it is infinitely more patient. For millions of years, gravity whispers to the cold molecules of a giant molecular cloud. It doesn't scream. It doesn't yank, simply nudges. It tells a single molecule of hydrogen to lean just a fraction of a millimeter closer to its neighbor. It is the longest, slowest flirtation in the universe, and it always ends in a crash. The stability of a molecular cloud is a delicate balancing act between two titanic physical forces: thermal pressure pushing outward and gravitational potential energy pulling inward. As long as these two forces are equal, the cloud remains in a state of hydrostatic equilibrium, surviving unchanged for eons. To break this equilibrium and kickstart the birth of a star, the cloud must cross a threshold defined by the British physicist Sir James Jeans, known as the Jeans mass, \BM m_. Once the Jeans mass is exceeded, the cloud experiences a phenomenon known as freefall collapse. In the initial stages, this collapse is isothermal, meaning the temperature stays exactly the same. Because the gas is still thin, any heat generated by the gravitational contraction can easily escape the cloud as infrared radiation. The cloud gets denser and denser, but it doesn't get hotter. As the density rises, the Jeans mass within smaller subregions of the cloud drops. This causes the massive cloud to break apart into smaller, independent pockets of collapsing gas, a process called fragmentation. A single giant molecular cloud doesn't just make one star. It fragments into thousands of individual pockets, each destined to become a star, a binary system, or a solar system of its own. We often experience moments in life where everything seems stable, almost permanently frozen in place. You work the same job, live in the same town, see the same faces. Then something shifts, a sudden loss, a chance meeting, a small realization. The balance is broken, and suddenly your life enters a period of rapid, terrifying freefall. It feels chaotic, but just like the fragmentation of a cosmic cloud, that collapse is often the only way new structures can form. We are terrified of falling because we fear the impact at the bottom. But the universe reminds us that falling is simply how something grander begins. We are children of gravity, bound to the earth by the same force that broke the ancient clouds apart so we could exist. If you look up at the Milky Way on a perfectly clear night, you will notice large, dark gashes cutting across the band of stars. It looks as if someone took a paintbrush dipped in black ink and smeared it across the sky. For centuries, ancient astronomers thought these were empty holes in the fabric of heaven, places where God simply forgot to put stars. They were completely wrong. Those dark patches are not empty. They are the busiest construction zones in the cosmos. They are completely packed with dust, hiding the violent birth of stars from our eyes like a heavy velvet curtain hanging over a stage. The ink blocking the light of distant stars is interstellar dust. These grains are tiny, typically less than a micrometer across, comparable to the particles found in cigarette smoke or fine soot. They are composed of heavy elements synthesized by ancient, long-dead generations of stars. Carbon in the form of graphite or polycyclic aromatic hydrocarbons, PAHs, silicates, essentially microscopic sand grains, and coatings of water ice, frozen carbon monoxide, and methane. When visible light from a background star hits these dust grains, it undergoes extinction and reddening. The dust grains are roughly the same size as the wavelength of blue light. Because of this, blue light is scattered and absorbed efficiently, while longer wavelengths of light, like red and infrared, can slip past the dust grains more easily. This is the exact same physics that causes our sunsets on Earth to look deep red. Inside a collapsing core, the concentration of this dust becomes so high that the region becomes completely opaque to visible light, forming what astronomers call a Bok globule. If you were to look at a Bok globule through a standard optical telescope, it would look like an ink drop on a sheet of glass. To see through this veil, modern astronomy relies on infrared telescopes like the James Webb Space Telescope, JWST. Infrared radiation has wavelengths long enough to bypass the microscopic dust grains without bouncing off them. By capturing this infrared light, scientists can peer directly into the heart of the dark cloud, revealing the glowing, embryonic star hidden deep within its dusty womb. There is something deeply human about the fact that the most important transformations happen in the dark, hidden from view. When we are going through our darkest moments, grief, reinvention, deep healing, we often isolate ourselves. We pull the blinds, we stay inside, we hide our faces from the world. Society looks at these periods of isolation as empty or wasted time, much like the ancient astronomers looking at the dark patches in the sky. But your dark periods are not empty. They are your own personal Bach globules. They are the times when your density is increasing, when you are gathering your thoughts, rebuilding your broken pieces out of sight, preparing for the moment you finally break through the dust and shine. There comes a point in every collapse where you simply cannot compress any further without something pushing back. Think of packing a suitcase for a long trip. At first, the clothes slide in easily, but as you add more, you have to push down harder. Eventually, you are sitting on the suitcase using all your weight, and the clothes are compressed into a solid, unyielding mass. In the heart of our collapsing cosmic cloud, a similar limit is reached. The gas has been falling inward for 100,000 years, but suddenly, the center says, "No more." It hardens, creating a distinct, solid heart inside a ghost. For the first few millennia of a cloud core's collapse, the process is easy and cool. The gas falls inward at supersonic speeds, and because the cloud is relatively transparent, it radiates away its gravitational energy as light. But nature always demands attacks on motion. As the density in the absolute center of the fragment skyrockets, reaching about \BM 10 carat minus 13 \text G/cm carat 3, an extraordinary transition occurs. The gas becomes optically thick. Suddenly, the infrared light generated by the falling matter can no longer find a clear path out of the cloud. It gets trapped, bouncing from molecule to molecule, dust grain to dust grain. Because the energy can no longer escape, the temperature in the core begins to spike dramatically. For the first time since the collapse began, this skyrocketing internal pressure becomes powerful enough to completely halt the free fall of matter in the center. This creates a stable, well-defined object known as the first hydrostatic core. This core is massive, typically containing about 1% to 5% of the sun's mass. But it is bloated, extending out to several times the size of our entire modern solar system. It is not yet a star, it is far too cold and weak, but it is the definitive boundary line. The runaway, chaotic collapse of the cloud has been tamed, replaced by an ordered, structural entity that has carved out its own identity distinct from the surrounding cosmic fog. Every single person reading this has a core, a set of non-negotiable boundaries, values, or truths that define who they are. We spend much of our youth letting external influences change us, falling inward, conforming to pressures, and drifting with the currents of life. But eventually, if you compress a human being enough, they hit their own hydrostatic limit. They find a boundary they refuse to let anyone cross. They discover what they are willing to fight for. This realization is often uncomfortable. It creates heat and friction with the world around them. But it is the moment you cease to be a collection of random influences and finally become a distinct, unyielding individual. A human baby's birth is marked by a loud, sudden cry, a sharp intake of breath that forces fluid out of the lungs and announces its independent existence to the world. A star has an equivalent moment, but instead of drawing air in, it tears its own internal structure apart to survive. When the core of the collapsing cloud hits a critical temperature, the very molecules of hydrogen are ripped to pieces. The core collapses a second time, shrinking down in a matter of days into a fierce, blindingly hot sphere. This is the protostar's first cry, a flash of energy that screams across the galaxy. The first hydrostatic core is a temporary shelter. As matter from the outer layers of the cloud continues to rain down onto it, the weight increases, and the internal temperature continues to climb. When the temperature deep within the core hits approximately 2000 Kelvin \BM 727 /circ /text C, a major chemical transformation takes place. At this extreme temperature, the kinetic energy of the gas is so high that molecular hydrogen \BM H_2 can no longer hold itself together. The bonds between the two hydrogen atoms snap, splitting them into single, isolated hydrogen atoms through a process called dissociation. Breaking these chemical bonds requires a massive amount of energy. The core absorbs the heat generated by gravity to break these bonds rather than using it to maintain its outward thermal pressure. With its thermal support suddenly vanishing, the core undergoes a catastrophic second collapse. This collapse happens at staggering speeds. In just a few centuries, a blink of an eye in cosmic time, the core shrinks from an object spanning astronomical units down to a sphere just a few times larger than our Sun. As it compresses into this much tighter space, the density scales up by orders of magnitude, and the temperature leaps from 2000 Kelvin to over 100,000 Kelvin. The core has officially shed its identity as a mere cloud fragment. It is now a protostar. It is not yet generating its own energy via nuclear fusion, but it is glowing intensely from the raw, converted energy of its own gravitational fall. Growth is rarely a smooth, continuous upward ramp. It almost always involves moments where your existing structure completely breaks down. Think of the transition from childhood to adulthood, or the painful rebuilding process after a catastrophic failure. To move to the next stage of your life, you often have to break the bonds of your old identity. It feels like a second collapse, a terrifying regression where everything you thought was stable falls apart. But the universe shows us that this breakdown is not structural failure. It is structural optimization. You must shrink away your bloat before you can build a core hot enough to light up the dark. If you pull the plug in a bathtub full of water, the water doesn't rush straight down the drain in a straight line. It spins, creating a swirling whirlpool that circles the drain faster and faster as it gets closer to the center. This isn't just a quirk of home plumbing. It is an unyielding law of cosmic geometry. When gas falls toward a newborn protostar, it cannot hit it head-on. Instead, it forms a massive, flat, spinning plate of superheated material. This is an accretion disk, the ultimate cosmic kitchen, where planets are cooked from the leftovers of a star's dinner. Why doesn't matter fall in a direct, straight line toward a protostar? The answer lies in a fundamental physics principle: the conservation of angular momentum. Because the original giant molecular cloud was spinning, even if only at a microscopic fraction of a millimeter per century, that rotation must be conserved as it shrinks. Think of an ice skater pulling their arms inward during a spin. As their radius \BM r decreases, their velocity \BM v must increase to keep \BM l constant. As the gas cloud collapses, its rotation accelerates dramatically. The gas falling along the rotational poles can drop straight down onto the protostar without any resistance, but the gas falling along the equator is pushed outward by centrifugal forces. The result is a dramatic flattening of the system, transforming a spherical cloud into a thin, rapidly spinning disk centered on the protostar, the accretion disk. Matter within this disk cannot simply drop onto the star. It must first lose its angular momentum. It does this through internal viscosity and friction. The inner layers of the disk spin faster than the outer layers, rubbing against each other and generating immense heat. This friction slows the gas down, allowing it to spiral slowly inward, like a coin circling a donation funnel, until it finally plummets onto the surface of the protostar, adding to its growing mass. We often start projects or phases of life with high ambitions, rushing directly toward our goals. But we quickly find ourselves caught in a vortex of delays, side quests, and daily routines. It feels like we are running in circles, spinning around our destination without ever reaching it. But that spinning serves an essential purpose. The accretion disk of your life is where you gain experience, where friction refines your raw ideas, and where the leftovers of your efforts begin to coalesce into unexpected structures, like friendships, new habits, or secondary skills. You aren't wasting time by circling. You are building the disk from which your future world will be born. If you look at an artist's rendering of a young star, it looks like a glowing spinning top with two massive, brilliant lasers shooting out of its top and bottom. These aren't small streams of gas. They are hypervelocity death rays of plasma, cutting across light years of space, tearing through anything in their path. It seems completely paradoxical. Why would an object that is desperately trying to pull matter inward using gravity suddenly shoot massive streams of matter outward into the void? The answer lies in the universe's ultimate control mechanism, magnetism. As the protostar and its accretion disk spin at breakneck speeds, they carry along an invisible passenger, a magnetic field. The gas in the inner disk is so hot that its atoms have been stripped of electrons, turning it into a highly conductive fluid known as plasma. In physics, the behavior of magnetic fields in a moving plasma is described by magnetohydrodynamics, MHD. Because plasma is an electrical conductor, it locks onto the magnetic field lines, a phenomenon known as flux freezing. As the accretion disk spins rapidly, it drags the magnetic field lines along with it, twisting them like fibers in a rope. As the field lines twist tighter and tighter, they form an ultradense, helical magnetic bottleneck along the star's rotational axis. The pressure from this twisted magnetic field becomes immense. When new plasma tries to spiral inward through the accretion disk, a significant fraction of it, up to 10%, gets intercepted by these magnetic tracks. Instead of falling onto the star, the plasma is funneled toward the poles and shot outward at supersonic speeds, often exceeding hundreds of kilometers per second. These are bipolar outflows or Herbig-Haro HH objects. These jets act as cosmic pressure valves. By blasting away a fraction of the matter, they carry away excess angular momentum from the disk, allowing the remaining gas to safely fall onto the star without spinning the star to pieces. To grow into something stable, you cannot simply take everything in. You must also learn how to expel what doesn't serve you. Think of stress, negative influences, or old habits. If you try to hold on to everything that comes your way, you will spin yourself apart from the sheer anxiety and pressure of it all. Our personal jets are our emotional outlets. Our creativity, our workouts, our vent sessions with trusted friends. They might look violent or dramatic from the outside, but they are essential safety valves. They dump the excess momentum and emotional weight so that our core can remain stable, focused, and healthy. There is a specific turbulent age in every human life where we stop being dependent children but aren't quite mature adults. Adolescence. It is an era defined by mood swings, rebellion, slammed doors, and chaotic energy. Stars go through the exact same phase, and it is called the T-Tauri phase. During this time, the young star becomes a volatile rebel, fluctuating in brightness wildly from day to day and throwing massive tantrums that blast away the very cloud that gave it life. It is the star's way of telling the universe, "I am independent now." Named after its prototype star, T-Tauri in the constellation Taurus, this phase represents a critical transition. The object is no longer a protostar hidden in darkness. It has accumulated enough mass to become a pre-main sequence star, visible to our optical telescopes. The physics of a T Tauri star is defined by instability. The star's core is hot, but it is not yet hot enough to sustain stable nuclear fusion. Instead, the star is still contracting under its own gravity, liberating gravitational potential energy to shine. This contraction creates massive, chaotic convection currents throughout the entire body of the star, similar to a boiling pot of thick soup. These churning currents twist and tangle the star's surface magnetic fields, leading to monstrous stellar flares that dwarf anything our modern sun can produce. This causes the star's luminosity to swing unpredictably by orders of magnitude over the course of just days or weeks. Simultaneously, the T Tauri star develops an exceptionally powerful, high-velocity stellar wind. This wind is a continuous stream of high-energy protons and electrons blasting outward from the star's corona. This wind acts like a leaf blower on a cosmic scale, pushing back against the remaining envelope of gas and dust that surrounds the system. The T Tauri phase is the definitive cleanup crew of astronomy, blowing away the murky fog of the original molecular cloud and exposing the newly minted star and its planetary disk to the cold eyes of the universe. Adolescence and periods of intense identity formation are messy. We push people away, we change our minds daily, and our moods swing like a pendulum. Parents often look at their teenagers and wonder what happened to the sweet, predictable child they used to know. But that chaotic rebellion is a mandatory biological and psychological milestone. Without that wild energy, the child would never develop the independence needed to survive on their own. If you are currently going through a chaotic phase where your life feels unpredictable and volatile, take heart. You are simply in your T Tauri phase. You are clearing away the old protective structures that you have outgrown so you can stand on your own 2 feet. Every second of every day, our sun releases more energy than millions of atomic bombs detonating simultaneously. It has done this for 4 billion years without stopping. Yet, this entire cosmic furnace depends on a trick that should be completely impossible according to classical physics. To ignite its fire, 2 protons, which naturally repel each other like the positive ends of 2 powerful magnets, must touch. They don't have the energy to do it. They never should. But they manage it anyway by simply defying reality and walking through a physical wall. This is quantum tunneling, the ultimate magic trick that lights up the sky. The definitive transition from a pre-main sequence star to a true, living star occurs when the central core temperature reaches a staggering 15 million Kelvin /BM 15,000,000 /circ/text C. At this extreme threshold, the density and thermal energy of the gas are so high that the atoms are completely stripped of their electrons, leaving behind a dense sea of bare protons, hydrogen nuclei. To generate energy, the star must fuse these protons together to form helium through a chain reaction called the proton-proton (pp) chain. However, there is a massive obstacle, the Coulomb barrier. Protons carry a positive electrical charge, and like charges repel each other with immense strength via the electromagnetic force. At 15 million Kelvin, the protons are moving incredibly fast, but classical physics calculations show that they still do not possess enough kinetic energy to overcome this electrostatic repulsion and get close enough for the strong nuclear force to take over. By all accounts of classical mechanics, stars should never light up. The universe should be dark. The savior of the universe is a weird quirk of subatomic physics called quantum tunneling. Because of the wave-particle duality described by quantum mechanics, a proton does not exist at a single, mathematically precise point in space. Instead, it exists as a wave of probabilities. When 2 high-energy protons crash against each other's electrostatic barriers, there is a tiny, non-zero probability, roughly 1 in /BM 10^28 collisions, that a proton's wave function will extend through the barrier, allowing it to instantly materialize on the other side. Once through, the strong nuclear force, which is incredibly powerful but operates only over subatomic distances, grabs the protons and locks them together. This process converts a tiny fraction of the proton's mass directly into pure, raw energy according to Einstein's famous equation. We often encounter obstacles in our lives that seem utterly insurmountable. Logic tells us we don't have the resources, the energy, or the strength to break through the walls built in front of us. The pressure feels too immense, and we feel like giving up. But the ignition of a star reminds us that when things are compressed enough, and when the pressure is at its absolute peak, breakthroughs can happen through pathways that logic could never predict. Sometimes you don't need to climb over the wall. You just have to trust that if you keep pushing with everything you have, a quantum leap will happen, and you will find yourself on the other side of your struggle glowing. After millions of years of chaotic collapse, violent explosions, blinding jets, and quantum miracles, the star finally achieves something truly beautiful: peace. It enters a state of perfect balance that will last for billions of years, providing the steady, unwavering warmth necessary for planets to cool, liquid oceans to form, and life to open its eyes for the very first time. The frantic, screaming infant has grown into a calm, reliable protector. This is the main sequence, the long golden afternoon of a star's life. When a star successfully ignites stable hydrogen fusion in its core, it achieves a lifelong state of balance called hydrostatic equilibrium. The star is now governed by two equal and opposing forces working in perfect harmony. On one side, you have the immense inward pull of gravity, trying to crush the star down into a single point. On the other side, you have the outward radiation pressure generated by the nuclear fusion reactions occurring in the core. If gravity begins to squeeze the core a bit too much, the temperature and density rise, which instantly boosts the rate of nuclear fusion. This extra energy pushes the star's layers back out. Conversely, if the core expands too much, the temperature drops, the fusion rate slows down, and gravity gently pulls the core back inward. This self-regulating cosmic thermostat keeps the star stable for an incredibly long time. The duration of this phase depends entirely on the star's mass. Our own sun is currently right in the middle of this beautiful golden era. It has been sitting comfortably in hydrostatic equilibrium for about 4.6 billion years, and it has enough hydrogen fuel in its core to maintain this balance for another 5 billion years to come. We live in a world that glorifies the hustle, the dramatic transformations, the chaotic birth phases of careers and relationships. We chase the high of the spark, the excitement of the new. But the ultimate goal of all that chaos is to find your own main sequence, your own sustainable, healthy balance. True maturity is not about burning out in a flash of frantic glory. It is about finding a lifestyle where your inner passion balances out the external pressures of the world. It is the steady, quiet warmth you provide to your family, your friends, and your community day in and day out. We endure the cold voids, the terrifying freefalls, and the volatile rebellions of our youth just to earn this beautiful, hard-won grace. The ability to stand steadily in the universe, casting our own light into the dark. The script of creation is written in the language of physics, but its poetry belongs entirely to us. Every star you see in the night sky went through this exact journey. They fought against the void, harnessed the gravity that tried to crush them, survived their own internal explosions, and found a way to turn a dark, freezing cloud into a fountain of light. And remember, because you are made of the heavy elements forged inside those very fires, you carry that exact same cosmic blueprint inside you. You are not just looking up at the stars. You are looking at your ancestors, built from the exact same dust, driven by the exact same fire, and bound to the exact same light. Imagine building a magnificent mansion, but the construction site is so choked with thick, swirling blinding dust and scaffolding that you can't even see the front door. For the first few million years of a solar system's life, the newborn star is trapped inside exactly such a chaotic mess. It is completely choked by the remnants of the very cloud that birthed it. If this dust stayed forever, the star would remain a hidden, suffocating furnace, and planets would never see the open sky. But a star is not a passive resident of its nebula. It is a fierce cosmic broom. With its first mature breaths, it sweeps its entire stellar neighborhood completely clean. When a star transitions from its volatile T-Tauri adolescence to the stable main sequence, its internal structure stabilizes, but its impact on its immediate environment scales up dramatically. The circumstellar envelope, the leftover shell of gas and dust that didn't fall into the accretion disk, is still hanging around, blocking light and trapping heat. To clear this envelope, the star utilizes two distinct physical mechanisms: radiation pressure and stellar winds. Radiation pressure is a consequence of electromagnetism. Photons carry momentum /BMP, which is related to their energy /BME, and the speed of light /BMC by the de Broglie relationship. When trillions of high-energy photons stream out of the newly ignited stellar core every second, they collide with the microscopic dust grains in the surrounding nebula. Each collision transfers a minuscule amount of outward momentum to the dust. Over hundreds of thousands of years, this continuous, relentless bombardment acts like a steady cosmic breeze, pushing the lighter gas molecules and small dust particles away from the star. Simultaneously, the star's magnetic field drives a powerful stellar wind, a stream of charged particles, protons and electrons, traveling at speeds ranging from 200 to 800 kilometers per second. This wind collides with the remaining gas in the accretion disk, accelerating it past the escape velocity of the system. Through this dual mechanism, the star clears out a massive hollow bubble in space centered on itself, a process known as photoevaporation. The dense, opaque cloud that once hid the protostar is completely stripped away, leaving behind a clean, pristine planetary system where the central star can finally shine across light years of empty space. Think about the process of moving into a new phase of your life, perhaps graduating from college, starting a new career, or recovering from a major life upheaval. At first, your mind is a cluttered, chaotic mess of leftover anxieties, old habits, and confusing emotional baggage from your past. You feel choked, unable to see the path ahead clearly. But as you find your footing and establish a stable routine, you naturally start clearing out that mental clutter. You cut ties with toxic environments, abandon old habits that no longer serve you, and organize your thoughts. You become the architect of your own mental space. Just like a young star clearing out its nebula, this sweeping process can feel destructive and cold to the things being pushed away, but it is the only way to create an open, bright space where you can truly be seen. If you throw a mixture of ice cubes, rocks, and plastic toys into a roaring campfire, they won't all behave the same way. The ice will instantly vaporize into steam, the plastic will melt into a puddle, but the rocks will sit right there in the embers, hot but completely solid. A newborn star acts as a giant, cosmic campfire for its surrounding planetary disk. It creates a fierce gradient of heat that completely sorts the matter of the solar system, ensuring that heavy rocks stay close to the heat, while delicate, icy worlds are banished to the frozen outer darkness. The accretion disk surrounding a main sequence star is not uniform. It possesses a steep thermal gradient. Close to the star, temperatures can exceed 2000 Kelvin, while at the outer edges of the disk, just a few dozen astronomical units, AU, away, the temperature drops below 50 Kelvin. This temperature profile dictates what types of chemical compounds can solidify at different distances from the star, a principle known as the condensation sequence. In the inner regions of the disk, close to the star, the thermal energy is far too high for volatile compounds like water, methane, and ammonia to exist as liquids or solids. They are instantly vaporized into gas and pushed outward by the solar wind. Only materials with exceptionally high melting points, such as metals, iron, nickel, and silicates, rock-forming minerals, can condense into solid grains. Because these heavy materials are relatively rare in the universe, the planets that form in this inner zone are small, dense, rocky worlds like Mercury, Venus, Earth, and Mars. The critical boundary line in this sorting process is called the frost line or snow line. It is the specific distance from the star where the temperature drops below approximately 150 Kelvin /BM-123 / circ /text C, allowing water ice to condense into solid crystals. This formula demonstrates that the temperature /BM-T drops predictably as the distance /BM-R from the star increases. Beyond the frost line, solid ice grains become incredibly abundant, outnumbering rocky grains by a factor of 10. This massive abundance of solid material allows planetary embryos to grow rapidly, reaching masses 10 times that of Earth in just a few million years. These massive rocky icy cores then possess enough gravity to pull in huge envelopes of hydrogen and helium gas directly from the disk, creating the gas giants: Jupiter, Saturn, Uranus, and Neptune. We often want to be everything to everyone, blending all aspects of our lives into one uniform mix. We want to bring our casual, relaxed home self into a high-stakes business meeting, or our cold, analytical professional self into our deep, emotional relationships. But a well-functioning life requires a thermal divide, a personal frost line. You must learn to sort your priorities, your boundaries, and your energies based on the environment you are in. Some spaces require you to be unyielding and solid like rock, while others require you to be fluid, adaptive, and soft. Recognizing where your personal frost line lies is not a sign of emotional compartmentalization. It is the ultimate mark of personal maturity, allowing you to build a complex, balanced life where every element has its correct, designated home. We like to think of our solar system as a peaceful, cosmic clockwork where planets glide smoothly along their orbits like trains on a track. But if you were to travel back in time to the infancy of our star, you would find yourself in a terrifying cosmic demolition derby. The sky would be filled with millions of jagged, mountain-sized rocks hurtling through space at supersonic speeds, smashing into each other with the force of thousands of nuclear bombs. This is the brutal process of planetary accretion, a chaotic era where planets are not carefully built by design, but are violently smashed together from the wreckage of endless cosmic car crashes. Once the star has sorted the raw materials of the disk via the frost line, the process of planet formation moves through three distinct phases: coagulation, runaway growth, and oligarchic growth. In the first phase, microscopic dust grains swirling in the accretion disk collide at very low velocities. At this scale, gravity is completely negligible. Instead, the grains hold together via weak van der Waals forces and electrostatic attraction, much like dust bunnies gathering under your bed. As these clumps grow to the size of pebbles and rocks, their structural integrity increases, and they begin to settle into the midplane of the disk. When these objects reach approximately 1 kilometer in diameter, they are classified as planetesimals. At this critical size, their mass becomes large enough for their own gravitational fields to influence neighboring matter. The planetesimals begin to pull each other into eccentric orbits, leading to a phase of runaway growth. The largest planetesimal in a given orbital zone will have a larger gravitational cross-section, allowing it to sweep up smaller rocks faster than its competitors, growing exponentially. Once the dominant objects, now called planetary embryos or protoplanets, have cleared out most of the small material in their immediate orbital feeding zones, growth slows down, entering the oligarchic phase. The system is now populated by a few dozen massive, competing bodies. The final stage of planet formation is marked by catastrophic giant impacts. The orbits of these protoplanets cross paths, leading to immense collisions that can entirely liquefy planetary crusts. A classic example of this occurred in our own solar system when a Mars-sized protoplanet named Theia smashed into the infant Earth, melting our world and ejecting the debris that would eventually coalesce into our moon. Think about the process of learning a deeply complex new skill, like playing the piano, coding, or navigating a complex emotional relationship. In the beginning, it feels like a chaotic series of failures and mental crashes. You make mistakes, you hit the wrong notes, you write buggy code, and you accidentally hurt the people you care about. It feels messy, uncoordinated, and deeply frustrating. But those mistakes are not a sign that you are failing. They are the planetary accretion of your character. Every failure is a collision that leaves behind an experienced grain. Over time, those grains stick together, building a solid foundation of wisdom. You cannot build a beautiful, stable life without surviving the demolition derby of your early attempts. If you have ever pushed a child on a backyard swing, you know that timing is absolutely everything. If you push at the wrong moment, you slam into the child's back and ruin the momentum. But if you push at the exact moment the swing reaches its peak, you add a perfect burst of energy, sending them higher and higher into the air. Planets dancing around a newborn star do the exact same thing to each other. By aligning their orbits in perfect mathematical ratios, they use their gravity to give each other regular, perfectly timed nudges, turning a chaotic mess of rocks into a beautiful, synchronized cosmic ballet. As planets grow inside the accretion disk, they do not remain stationary. The gravitational drag from the remaining gas and dust causes them to drift inward or outward, a phenomenon known as planetary migration. Left unchecked, this migration would cause planets to spiral directly into the central star or crash into each other, destroying the entire system. The savior of planetary architecture is orbital resonance. An orbital resonance occurs when two or more planets exert a regular, periodic gravitational influence on each other because their orbital periods are related by a ratio of small integers. For example, a 2:1 resonance means that for every 2 times the inner planet completes an orbit around the star, the outer planet completes exactly 1 orbit. When planets enter these resonant configurations, their mutual gravitational interactions occur at the exact same points in space over and over again. This regular timing can either destabilize the orbits, clearing out empty gaps in the system, like the Cassini division in Saturn's rings or Kirkwood gaps in the asteroid belt, or it can lock the planets into an exceptionally stable, self-correcting configuration. In our own solar system, Jupiter and Saturn once entered a 3:2 orbital resonance, an event that reshaped the entire layout of the outer solar system, flinging the icy planetesimals inward to deliver water to the infant Earth during a period known as the Late Heavy Bombardment. This delicate gravitational choreography is what ensures that planetary systems can survive stable for billions of years without falling apart. We do not live our lives in isolation. We are constantly orbiting around other people, our family members, our romantic partners, our co-workers, and our friends. In the beginning, these relationships can feel unstable, with people crashing into each other's boundaries, creating friction and emotional drama. But as you spend time together, you naturally begin to adjust your schedules, your communication styles, and your expectations. You find a rhythm. You establish a personal orbital resonance. You figure out exactly when to offer support and when to give each other space. This shared choreography is what transforms a collection of volatile individuals into a stable, lifelong community. True harmony is not about being identical. It is about finding a beautiful, synchronized rhythm that allows everyone to shine without crashing into each other. If you walked onto the surface of a newborn rocky planet just after its accretion phase, you would find yourself standing on a hellish, glowing ocean of liquid rock, breathing a toxic soup of vaporized metals and sulfur. It would be an environment completely hostile to any form of life. Yet, right beneath that bubbling lava ocean, the planet is hiding a magnificent secret. As the planet cools, it begins to sweat. It releases gases trapped deep within its mantle, creating a thick, protective blanket of air that wraps around the world like a warm coat, shielding it from the harsh, cold reality of open space. The atmosphere of a young planet evolves through two distinct stages: the primary atmosphere and the secondary atmosphere. The primary atmosphere is gathered directly from the primordial solar nebula during the planet's early growth. Because the nebula is overwhelmingly composed of hydrogen and helium, the infant planet wraps itself in a lightweight envelope of these light gases. However, for small rocky planets close to the star, their surface gravity is too weak and the stellar wind is too intense. The high thermal energy causes these light gases to easily exceed the planet's escape velocity, causing the primary atmosphere to bleed away into space. The atmosphere we actually breathe today is a secondary atmosphere, created through a physical process called volcanic outgassing. As the planet's molten interior begins to cool and solidify, volatile compounds that were trapped inside the rocky planetesimals during accretion are forced out of solution. Volcanoes and deep fissures erupt across the cooling crust, releasing massive quantities of water vapor, \BM, H_20, carbon dioxide, \BM, CO_2, nitrogen, \BM, N_2, and sulfur compounds into the sky. Additionally, this early atmosphere is continuously replenished by external impacts. Comets and volatile-rich asteroids originating from beyond the frost line rain down on the planet, vaporizing upon impact and contributing massive quantities of water and organic molecules to the growing air supply. Over millions of years, as the surface temperature drops further, the water vapor in this secondary atmosphere condenses into liquid droplets, falling as rain for centuries to fill the first primordial oceans, while the stable nitrogen and carbon dioxide gases remain behind to create a dense, protective atmospheric shield. We are all born with a primary atmosphere, the default beliefs, values, and worldviews handed down to us by our parents, our schools, and our immediate childhood environments. Protects us early on, but as we step out into the harsh, competitive world, that borrowed shield often burns away. It isn't strong enough to withstand the friction of adult reality. To survive, you have to build your own secondary atmosphere. You have to go deep inside yourself, doing the heavy internal work to figure out what you uniquely believe, what you value, and who you actually want to be. This internal outgassing can be painful and explosive. It requires you to confront your own hidden depths and volcanic emotions. But it is the only way to build a personal shield that is uniquely yours, creating a safe, healthy environment where your own hopes and dreams can finally take root and grow. A star is a beautiful, life-giving creator, but it is also a terrifying cosmic executioner. Every second, it blasts out an invisible, toxic stream of high-energy radiation and charged plasma that can easily strip a planet's atmosphere away, leaving it a dry, dead, barren desert like Mars. To survive this relentless solar bombardment, a planet cannot rely on its rocks or its oceans. It must generate its own invisible subatomic armor. Deep within its white-hot iron core, a planetary dynamo creates a massive magnetic shield that wraps around the world, turning the deadly solar wind into a beautiful, harmless light show. The survival of a planet's atmosphere and potential biosphere depends heavily on the presence of a magnetosphere, a region of space surrounding the planet where the dominant magnetic field is generated by the planet. internal structure rather than by space currents. To generate this magnetic shield, the planet must possess an active planetary dynamo. This dynamo requires three precise physical ingredients: a large interior volume of electrically conducting fluid, such as a molten iron-nickel outer core, thermal energy driving convective fluid motion within that liquid core, a rotational force, the Coriolis effect, to twist those convective currents into organized helical columns. As heat escapes from the solid inner core of the planet, the molten iron in the outer core expands, becomes less dense, and rises toward the mantle. As it rises, the rotation of the planet spins these rising iron streams into tight, spinning cylinders. Because molten iron is an excellent electrical conductor, these moving fluid columns act like giant, subterranean electrical wires, generating massive electrical currents through induction. According to Ampere's law, these moving electrical currents generate a powerful global magnetic field. This global magnetic field extends far out into space, creating an invisible teardrop-shaped shield called the magnetosphere. When the high-velocity ions of the solar wind strike the shield, they are forced to deflect around the planet via the Lorentz force, sliding harmlessly past the world into the deep void of space. The only places these charged particles can penetrate are the magnetic poles, where they collide with upper atmosphere gases to create the stunning celestial light shows we call the auroras, northern and southern lights. In life, we are constantly bombarded by external stresses, criticisms, and negative energies from the world around us. If you don't have a shield, these external currents will slowly erode your self-confidence, strip away your peace of mind, and leave you feeling emotionally spent and hollowed out. You cannot stop the world from throwing its storms at you, just as a planet cannot stop its star from blowing its solar wind. Your defense must come from within. You must build your own internal dynamo, a core of self-worth, resilience, and personal boundaries that keeps you centered no matter how chaotic the external world gets. This invisible shield doesn't isolate you from reality. Instead, it gracefully converts the harsh criticisms and negative energies directed at you into harmless, beautiful moments of personal growth and self-reflection. Imagine a busy, crowded train station where millions of people are rushing around in every direction without any lanes or signs. It's an absolute mess of accidental bumps and near misses. But slowly, over several hours, the security guards steer people into organized lines, the trains leave with their passengers, and the station floor becomes perfectly clean and calm. This is exactly what happens during the final cleanup phase of a new solar system. After millions of years of chaotic planet building, the system undergoes its final cosmic sweeping process, locking the surviving worlds into their permanent orbits and flinging the remaining garbage out into the dark. The final phase of a solar system's birth is characterized by dynamical clearing. Even after the main planets have fully formed, the system is still littered with trillions of leftover planetesimals, asteroids, and comets. This debris constitutes a significant gravitational drag on the system, creating small orbital instabilities. To achieve long-term architectural stability, the major planets use a mechanism called gravitational scattering. When a small asteroid passes close to a massive planet like Jupiter, it experiences a close gravitational encounter. The planet transfers a small fraction of its orbital kinetic energy to the tiny asteroid, acting like a cosmic slingshot. Depending on the angle of approach, the asteroid is either slung inward toward the inner solar system or blasted outward into deep space. This dynamical clearing reached its peak in our solar system roughly 3.9 billion years ago during an event called the Late Heavy Bombardment. During this era, planetary migrations shifted the orbits of Jupiter and Saturn, destabilizing the ancient asteroid belts. A torrent of space rocks was slung inward, cratering the surfaces of the Moon, Mars, and Mercury, while simultaneously delivering water-rich materials to Earth. The debris that was slung outward didn't escape the star's gravity entirely. Instead, it accumulated in two massive, frozen structural reservoirs at the outer edge of the system. The Kuiper Belt, a flat disk of icy bodies extending from the orbit of Neptune out to about 50 AU. The Oort cloud, a massive, spherical shell of comets wrapping around the entire solar system at distances up to 100,000 AU. Once this remaining debris was either swept up by impacts or safely stored in these distant reservoirs, the planetary system achieved dynamic stability, transforming a volatile war zone into a clean, highly ordered celestial home. As we grow older, we naturally go through a period of personal cleanup. In our youth, our lives are cluttered with hundreds of acquaintances, erratic goals, chaotic habits, and disorganized ambitions. We try to explore every single pathway simultaneously, which often results in endless internal emotional collisions and personal burnout. But as you mature, you realize you cannot hold on to everything. You start organizing your life. You let go of superficial friendships, abandon projects that don't align with your core values, and streamline your focus. You delegate some memories to the distant past and lock your energy onto a few meaningful long-term goals. This pruning process can feel lonely at first, but it is the only way to transform a frantic, scattered existence into a balanced, clear life built to endure. If you look at two identical twins, they might look exactly the same from across the room, but if you look closer, their fingerprints will reveal two entirely unique identities shaped by their individual journeys. Stars behave exactly the same way. From a distance, every yellow star looks just like our sun. But if you take their light and pass it through a glass prism, you will reveal a beautiful, hidden barcode of dark lines cutting across the rainbow. This is the star's stellar signature, an uncopyable cosmic fingerprint that tells the story of every single atom it inherited from its ancient birth cloud. Every star possesses a unique chemical identity that can be unlocked through a scientific technique called spectroscopy. When a star shines, the white light generated deep within its hot core passes outward through its cooler, outer atmospheric layer, the photosphere. The atoms of various chemical elements present in the photosphere, such as iron, magnesium, sodium, calcium, and titanium, absorb very specific wavelengths of light. This absorption occurs because electrons can only transition between discrete energy levels, \BM_, within an atom. When an incoming photon possesses an energy, \BME equals H\nu, that matches the difference between two electronic energy states, the photon is absorbed, kicking the electron to a higher orbit. As a result, when we capture a star's light with a telescope and split it into a rainbow spectrum using a spectrograph, we see a series of dark, narrow gaps cutting across the colors. These are called Fraunhofer absorption lines, because each chemical element has a unique arrangement of electrons. Each element leaves behind a completely distinct pattern of lines, a chemical barcode. By analyzing the position and depth of these lines, astronomers can determine the exact chemical composition, temperature, density, and rotational velocity of a star light years away. This chemical profile is called the star's metallicity, a permanent cosmic signature inherited directly from the specific fragment of the molecular cloud that birthed it. Every single person carries a personal signature, a mosaic of quirks, values, scars, and passions that defines who they are. This signature is your individual barcode, forged from every single experience you have ever lived through. It contains the books you read, the setbacks you survived, the people who loved you, and the places that broke your heart. You cannot alter your history, nor should you want to. Your unique barcode is what distinguishes you from the billions of other people walking this planet. It is your distinctive perspective, your creative voice, and your authentic self. The universe doesn't need you to be a flawless copy of someone else. It needs you to wear your unique signature proudly, casting your own distinctive light into the world. If you sit too close to a roaring winter campfire, your face will get scorched and your skin will blister. If you sit too far away, you will shiver in the dark, freezing cold. To stay comfortable, you have to find that perfect, cozy middle spot where the warmth is just right. A newly minted star creates exactly such a comfort zone in space for its surrounding planetary family. This is the habitable zone, the ultimate cosmic sweet spot where a planet is neither a boiling desert nor a frozen icebox, creating a safe planetary cradle where liquid water can pool and life can finally open its eyes. The Circumstellar Habitable Zone, HZ, colloquially known as the Goldilocks Zone, is the theoretical spherical region surrounding a star where the atmospheric pressure of a planet can support liquid water on its surface for extended periods. Conversely, a small, cool red dwarf star, M-type, will have a tiny luminosity, meaning its habitable zone will be located incredibly close to the star's surface. The inner edge of the habitable zone is defined by the threshold where a planet experiences a runaway greenhouse effect. If a planet orbits too close to the star, the intense incoming solar flux vaporizes the oceans into steam. Because water vapor is a powerful greenhouse gas, this steam traps even more heat, accelerating evaporation until the oceans are entirely gone, leaving behind a scorching wasteland like modern Venus. The outer edge of the zone is defined by the maximum greenhouse limit. Beyond this boundary, the stellar radiation is so weak that even a thick atmosphere of carbon dioxide cannot trap enough heat to prevent water from freezing solid. The oceans turn to ice, locking the planet into a permanent, global glaciation state. Only planets that find themselves securely parked in the stable middle ground between these two extremes can maintain liquid oceans, providing the ultimate chemical matrix required for organic molecules to assemble into the first living cells. We spend much of our lives swinging between extremes. We bounce from working ourselves to the bone of exhaustion to falling into long slumps of unmotivated laziness. We oscillate from being overly emotionally dependent on others to completely shutting down and isolating ourselves in our own private worlds. These extreme swings are exhausting, leaving us feeling burned out or cold inside. Growth is about discovering your own personal Goldilocks zone. It is about finding that healthy balance where you are working hard but taking time to rest, and where you are building deep connections with others while preserving your own independent identity. Finding this emotional sweet spot is not a static achievement. It is a lifelong, active balancing act. But it is the only way to build a sustainable, healthy mental space where your creativity, your relationships, and your true self can open up, thrive, and bloom. When a massive tree in an ancient forest grows old and falls to the ground, its story does not end there. Its wood decays, releasing vital nutrients back into the soil, creating a rich nursery bed where thousands of tiny new saplings can take root and grow toward the sun. The universe operates on the exact same beautiful recycling principle. A star is born, lives for billions of years, and eventually dies, scattering its enriched ashes back into the galactic void. This means the story of a star's birth is not an isolated event with a definitive beginning and end. It is a grand, unending loop where every single death is the secret seed for the next generation of light. We are deeply terrified of endings. We fear the conclusion of relationships, the retirement from careers, the loss of youth, and ultimately our own mortality. We look at endings as a final defeat. But the grand biography of the stars offers us a far more beautiful, grounded perspective. Nothing in the universe is ever truly lost or wasted. The efforts you make, the love you share, the lessons you learn, and the art you create are never erased when a phase of your life ends. They become the enriched dust of your character, drifting into your future, laying down the groundwork from which your next grand chapter will grow. You are part of an eternal, beautiful loop of creation and reinvention. You are built from the ashes of ancient, long-dead suns, and the fire you carry inside you right now will eventually light up the worlds of generations yet to come. If these calm explorations help you unwind, you might also like, subscribe, or leave a thought below. It helps other sleepy souls find their way here, too. For now, let your thoughts settle and let the night carry you the rest of the way. Sleep well and good night.